you have 10 minutes for your presentation. I will give you 2 minute warning before the end. Okay, let's start.
Good morning, good afternoon, professors. I'm Kwan Chong Han, Kevin, from Sir Ellis Kadoorie Secondary School, West Kowloon. My team registration number is 100095. My investigation topic is towards Kowloon's conjecture. Kowloon's conjecture was first stated by French-Belgian mathematician Eugene Charles Kowloon in the year 1844, and he conjectured that the only consecutive perfect powers are 8 and 9, or in the term of the Van equation, the only positive integral solution of this equation, x to the power r minus y to the power s is equal to 1, is 3223. For the later 160 years, numerous results, including those particular and weaker results, have been established, and using advanced algebraic number theory. And finally, this conjecture has become a theorem in 2002 by Romanian mathematician Predan Mihailescu. And are there any elementary ways to carry out investigation on Kowloon's conjecture? And that's my major motivation on this project. And firstly, observe that Kowloon's conjecture involved a 4-variable exponential Diophantine equation, which has so many free variables. So I used the strategy of looking at simpler cases. That is, reduce the number of constraints of the original equation, and then obtain weaker results, and then extend to stronger and broader results. My investigation process is divided into 3 stages. Stage 1, using common techniques in solving the Diophantine equations. Stage 2, using several lemmas to obtain broader results. And Stage 3, extension of Kowloon's conjecture. And elementary techniques such as factorization and modular arithmetic are used. And I start from 2-variable cases, which is considered to be the simplest cases. And theorem 1, 3 to the power m minus 2 to the power n equal to 1 has only one positive integer, and this is the simplest case. And I use the lemma 3 to the power a is congruent to 1 modulo 8 implies a is an even integer. And by contrapositive, I can obtain this lemma easily. And the proof of theorem 1, for n is greater than or equal to 3, taking modulo 8 to both sides, I get 3 to the power m is congruent to 1 modulo 8. So by the lemma, m is even, and so that I can factorize the statement. And because left-hand side is a prime factorization, I get the expressions in asterisk, and consequently, I can get AB equal to 2, 1, and Mn is 2, 3. And similarly, I can obtain the following theorems, and theorem 2 and theorem 3. The 2-variable cases can be obtained easily by elementary knowledge, except this one, because there is no expression of prime factorization involved. So can we use our approach to 3-variable cases? And the answer is positive. This is theorem 4, p to the power x minus y to the power p equal to 1, where p is a prime. Firstly, I check the case for p equal to 2, and for x is greater than or equal to 3, y squared is congruent to negative 1 modulo 8, which is impossible because y squared always congruent to 0 and 1 modulo 8. So p equal to 2 gives no solution. And odd prime p, 1 plus y to a prime p, or I can factorize this. And then I collect all the ones and divide both sides by p. And I divide the subsequent process into 4 cases. Firstly, a and b are both greater than or equal to 2. And left-hand side is not divisible by p, but right-hand side does, so contradiction. And for the second case, take note, I collect the constant terms. Take note of the expression in square brackets. It is not divisible by p for p greater than 3. So again, contradiction. For case 3, I prove the claim b is greater than or equal to a. And in the red boxes, b is greater than a means that the expression below is greater than that above. So I get this one. And then using derivative test, in inequality, I can prove that these cases also give no solution. And then by checking, I give only this solution. How about using two broader results? I failed to get the results using this method for these 2 equations. However, if I consider the odd-even parity as well, I get successful to get some solution. For example, this. And I can extend this to this equation. And because x is a positive odd integers, the number of terms y in the second bracket has to be even as well. And using the same technique, factorization, I get the solution. And for the stage 2, we have a key observation. That is, Kowloon's conjecture can be rewritten to involve the expressions 1 plus or minus x to the power n. And this is a very important property, in my opinion. And I have 3 attempts. The first one is factoring lemma. The second one is LTE lemma. And the third one is Mondi's theorem. I use lemma 2 and lemma 3 mainly. For the LTE lemma, it deals with the prime p, the largest power prime p in the prime factorization of positive integer x. I denote this by VPX, and I have this LTE lemma just by simple modular arithmetic and induction. Also, I can give a much simpler proof of theorem 4. And x, the key is the square box, and the rest square box. X is equal to v sub p 1 plus y plus 1, and so that the expression of the expression in the blue bracket, and I can get is the order of p is 1. So that simply done by derivative test, and I can get the solution. And however, LTE is simple, but I get a more useful lemma. It's called the Zsigmondy's theorem. The working principle of Zsigmondy's theorem is that we can prove that the equation does not hold for a large number of cases. We only have to check those exception cases. For example, in the part 1 of Zsigmondy's theorem, A equal to 2, B equal to 1, and N equal to 6. And in 2, A equal to 2 and B equal to 1. So in theorem 6, this is an unproved case in stage 1. I can obtain the proof easily by Zsigmondy's theorem. Firstly, for the general cases, there must exist a prime p such that p divides 1 plus x to the power s z, but not 1 plus x. So left-hand side is not divisible by p, but right-hand side does. So contradiction. Only need to check the case of x equal to 2 and z equal to 3. And some similar results can be obtained. And theorem 8 and theorem 9. And observe that theorem 9, although we can check the exception cases, however, that means this one, the Zsigmondy's theorem 1.2, and in fact we have to do some more process to prove it, but it is much simpler than the previous one. And in stage 3, I extend the Kowloon's conjecture by replacing one of the Kowloon equation by arbitrary positive integers n. That is this one. And in general, it is expected to be more difficult because it is not easy to factorize part of the expressions, and as well as very difficult to use the Zsigmondy's theorem. And I can obtain some weaker results. For example, theorem 10 is considered, you construct with the cubic n, is this equation. And the proof 1, the first method, using Fermat's method of descent, as mentioned in my report. But there are some disadvantages. For example, it cannot incorporate the case of p equal to 2 and 3 into the proof. And I need other methods to deal with these two cases. And it is long and tedious, and need to be divided into several cases, and more lemmas are required. But however, by Zsigmondy's theorem, it is much simpler. And for case 1, I have to check the A equal to B case first because it is not included in the Zsigmondy's theorem, and it is simple. I get only one solution set. And for case 2, I assume that A is greater than B, and by Zsigmondy's theorem, for the general cases as the same as before, and it uses contradiction, and it remains to consider the exception case A equal to 2 and B equal to 1, and consequently I obtain the only solution set A, B, P, N. And for theorem 11, I consider the more general power of the N, and has a unique solution. And firstly, we have to prove that K is odd, so that x to the power K plus y to the power K can be factorized. And again, by Zsigmondy's theorem, as well as theorem 1, we can obtain that there are totally four solution sets. And how to prove that K is odd? In fact, it is just simply by modular arithmetic, as well as consider the GCD, the greatest common divisor. And conclusion, although a number of particular cases of Kowloon's conjecture has been obtained, it is far from the end of my investigation. For example, can the condition P is prime be weakened? Can any broader results be obtained? Also, there are some results I have do investigation but not successful. For example, how about the consecutive powers? That means the R and S in the Kowloon's conjecture. Is it also true? Can it be done by elementary method? Also, it is clear that there is a huge margin in the extended Kowloon's conjecture, and the results in stage 3 are still very weak. And that's the end of my presentation. Thank you.